Okay, this is 8.31 for Math 21B, and this will basically be the lecture for this time. And you guys will have to look at this on YouTube and fill it out on your own. During class, I will have a conference via Zoom or the conference button that's on Canvas, and then everyone can log in and ask me questions from this section if you have any. Okay, great, so let's just get into it. Okay, so none of us should text while we drive. Some research suggests that women text more while they drive than men do. Other research says that men text more than women while they drive. Suppose we're interested in investigating the texting behavior of men and women drivers. After making some observation, we began to think that men send more texts while they drive than women. To investigate the possibility that men send more texts while they drive than women, we randomly sampled the populations of men and women who text while they drive. So we have here 85 men and 97 women who text while they drive. So we find that 31 of the men and 22 of the women text frequently. And so this means that they regularly send 7 or more text messages per week while they drive. So let's do a test of the difference in two population proportion using our texting behavior. Okay, so let's do step 1. Remember we have the different steps, right? Step 1 being determine the hypotheses. So let's determine the null and the hypotheses. So the null hypothesis, remember that it's no change. Right, so the population proportions are equal. So remember, that's the H naught, that's no change. You can think of it as zero change, and the proportion remains the same. The alternative hypothesis is this claim that the population proportion of men who text frequently while they drive is larger than the population proportion of women who text frequently while they drive. Okay, so we would like to do that. So, so in order to say two population, the difference is 0, remember that means that they're equal, okay? All right, so let's see here. So we want to test that claim. And so what's the parameter in this test? The parameter is the difference in population proportions, okay? So here we go. So remember that, we're basically going through the same stuff that we have before, okay, except we're going to use what's called a pool proportion in this case. We're going to assume that the null hypothesis is true, and then we're going to test it, okay? So write a sentence for null hypothesis in terms of difference in the population proportion. Okay, so null hypothesis would be the difference in proportions of men and women who text frequently while driving is 0. And so here, if you need to push pause, you can go ahead and pause this. This is a video, so feel free to do that. Okay, so let's continue. Can we write a sentence for the alternative hypothesis in terms of the difference of population proportions? Okay, so think about this, right? What's the claim? The claim is that the proportion of men who text frequency is greater than the proportion of women who do, right? So the claim is that the portion of men who text frequently while driving, not just text in general while driving, is greater than the proportion of women who do. That's proportion of women who do. In other words, the difference, so because it says in terms of the difference. So basically if you have PM greater than PF, so let's subtract PF from both sides, minus PF minus PF, you would get that the difference of the proportion of men and women, the difference is going to be greater than 0. Okay? So the difference, because it says to write a sentence, in proportions of men and women who text frequently while driving, is greater than 0. Okay. All right. So next, we can determine whether the sample statistics satisfy the normality criteria and calculate the sample proportions and the difference between the sample proportions. Okay? So first thing is we need to test the normality criteria, right? So for men, we have to verify that each sample contains at least 10 successes and 10 failures, right? So going back to the original problem, we have how many successes for men and how many failures for men and women. So that's right here, right? So we see here, we have a total of, right, NM and F, right, of 85 and 97 women tested. Here, 31 of the men test frequently and 22 of the women. So that would be a success, right? So for the men, there are 31 successes, and then 85 minus 31 would give you the 54 failures, right? Or in other words, non-successes. And then for women, 22 of them texted frequently while driving, and subtracting that from the total, which would be 97, you obtain 75 failures. Okay? So are these values large enough to assume approximate normality of the underlying sampling distributions? Why or why not? And then we would say, yes, the normality criteria is satisfied. Or the criteria for normality are satisfied. Okay. All right. So let's have some fun here and calculate the sample statistics. So what would be P hat M? Remember, P hat is a sample proportion, right? So it would be approximately 31 out of 85. Which is approximately 0.365. Okay? So for women, you can pause it here if you want to try to answer it on your own. You can pause this anytime, of course. You have 22 out of 97, which is 0.227. Okay? And then if we compute the difference, we're basically just subtracting, right? We're saying 0.365 minus 0.227, which is approximately 0.138. Okay, and that's the difference in the proportions. Okay, let's move on. Step 3, assess the evidence. So what are we testing here? We're testing the difference in population proportions of men and women who text while driving. Okay, so the statistic will be our z-score of the observed difference. Okay, so here's what we need to do in order to do that. So So we have, remember the null hypothesis is a claim that the proportions are equal. Okay, if we have this, we assume, remember when we do testing, right, hypothesis testing, we always assume that the null hypothesis is correct, right? That's the whole idea. We're under the assumption that the null is true. We go ahead and we run through our testing, and then we find the percentage of the probability of getting a specific value, right? And we compare it to alpha, and we figure out the level of significance and all that. So this is kind of what we're barely in the first step, okay? So we're saying, okay, we can say that we can combine the samples together to create this single proportion P bar, okay? This P bar is called pooled estimate, okay? So let's do that. Let's calculate the pooled estimate, okay? So basically, how do you do that? Okay, so how do we do that is basically we add the X's, all the successes, and we divide that by the total number of trials, right? Or N sample size, right? So in this case, we get approximately 0.291. Okay? All right. So now we need to do the standard error. Okay? So the standard error, so we're very familiar with this. So the standard error here, it has a different formula, but not too different. We're using the pooled proportion, but we're dividing it by the number of men, and then we're adding it to the same P bar, 1 minus P bar, and then dividing it by the number of women. So see here, that's P bar, 1 minus P bar divided by 85, which is the number of men, plus P bar, 1 minus P bar, times the quantity 1 minus P bar divided by the number of women, that's 97. And then we put that in here and we square root the whole thing and we get 0.067. Okay? Great. All right, so now we have here a collection of differences. And this is a simulation right here in this dot plot. Let's say we have this dot plot here. So we're showing this dot plot shows a large number of differences from similar samples, okay? So that way we can kind of see if it's usual or unusual, okay? So you see here, so each point represents a difference in the proportions of men and women who text frequently while driving, okay? So the men are collected from samples of 85 randomly selected men, and the women are computed, the proportion for the women are computed from samples of size 97. Okay? So the assumption is that, so remember the assumption means that the distribution of, the assumption that the population proportions are equal will yield a distribution whose mean appears to be 0. Okay, so let's see here. We're going to place a difference on the dot plot above. Is the difference observed in the sample data unusual? Okay, so from 3C was 0.138. So let's graph that. Okay, so graph that here. We have P hat men, P hat women is 0.138, right? Gosh, I forgot it again. 0.138. So where would that go? That would actually go, let's see, 0.12, 0.16, maybe like about halfway between them. We have 0.1, 4, I guess would be here. So like maybe like right here, right? 0.138. Okay. So it's over here, right? Here's the middle. Here's the center, 0. It's kind of far away, right? It's a bit away. Okay. So it appears to be unusual, yes. It appears far from the center. Right? It appears far from the center. Okay, so now we have to convert to a p-score here, right? So remember, the z-score, sorry, I said p-score. Z-score is kind of like a standard. We're standardizing this this value of differences, okay, the sample difference. And we're going to do that. Okay, I don't know where I was because I just paused that. Okay, we're finding the z-score. So here's the formula. So basically, like before, we have the difference in the sample proportions minus the difference in the population proportions divided by the standard error, okay? But in this case, so I mean, like in most every case, our assumption is that the difference is 0, right? That's the null hypothesis, so that's what we're doing. So to compute this, we would get what? Okay, so from previous, we have the standard error is 0.067, and we need this, and also we have that p hat m minus p hat w is 0.138. So let's go ahead and plug everything in. So we have 0.138 minus 0 divided by 0.067, and that approximately, that actually becomes 2.06, okay? Does the z-score appear high or low? And you remember what the definition of a z-score is? Okay, showing over here. Okay, so what's the definition of z-score, right? It's the number of errors above or below the mean, right? Which is 0, okay? So that represents the z-score. That's what the z-score is. Now in this case, what is usual? So remember that if it's within a z-score of 2 or below, right? Or higher than a -2, so between -2 and +2, if it's inside that region, it's considered okay. You know, that's about 95% of the data. That's fine. But if it's higher than 2 or 2, it's high. Okay, so this is unusually high. Even if it's just a little bit, it's still okay. Because it's 2 standard errors. Standard errors above 0. Okay? Alright. So now we use a p-value to determine whether this z-score indicates that the observed difference in sample proportion is largely different from the assumed mean. Okay? So remember, we have, what is it before? The p-value is the probability of observing a z-score that's either at least as extreme as the test statistic, right? So assuming the null hypothesis, what are the odds? What is the probability of us obtaining this sample, particular sample proportion? And if it's very small, right? If it's very small, it's a very small chance of this happening, then we say that we reject the null hypothesis, and we call this significant, right? It has to be p-value, has to be less than or equal to alpha. Remember that? And alpha is dependent on what level of significance we're talking about here. Okay, fine, let's go. So for a right tail test, the p-value is the probability of observing a z-score that is greater than the test, okay? So we need to find p-value of z greater than 2.06, okay? So how do we do that? Okay, we know I don't have my super cool calculator with me, so I have a different calculator that I guess we'll be using from now on. I have this one. I don't know if you guys can see that. Let's see, hold on, nope. See here. Can you see that? Kind of, it's kind of a weird, okay. So we want second distribution, right? Right, we have our norm CDF, and we have 2.06, comma, and then the upper, which is 999, right? And here we go. So I obtain a p-value of 0.0197, approximately 0.0197. This is a 7. I don't know why I wrote a Z. Okay. So just for reference, I used the function normal CDF, and I put my lower value, comma, and then just, you know, a very large number because it's going to the right, and that's what I got. Okay. So, what does that mean? Okay, what does that mean? To say, okay, to say that we have a true null hypothesis. So assuming sorry, I got all confused here. There is a very small chance of obtaining a difference in sample proportions of 0.138 or more from random samples of size 85 for men and size 97 for women. Okay. So suppose we conduct this hypothesis test at the 5% level of significance. Okay, so basically we're asking, is the value of P less than alpha? But in this case, because our level of significance is 5%, that indicates that alpha is 0.05. Okay, so what did we get for our p-value? We got 0.197, 197, and that's definitely less than 0.05. So yes, since p value is less than alpha, you can say that the observed difference in sample proportions (138) is statistically significant. since it's unlikely. It's unlikely. With the assumption HO. Oh, sorry. Okay. Okay, so then it says, using the p-value above and the level of significance, what can we conclude about the null hypothesis? So we can reject, right, the null hypothesis that the proportions are equal. And what can we conclude about the alternative hypothesis? So we would say that there's enough evidence to support the alternative hypothesis. To support the alternative hypothesis, that the proportion of men who text frequently while driving is greater than the proportion of women who text frequently. I don't know, well, while driving. Okay? And so now this is interpret. So let's interpret, right? So we know that we're supporting the alternative hypothesis. So we can basically say at a 5% level of significance, the sample statistic support the alternative hypothesis that the proportion of men who text frequently while driving is greater than the proportion of women, right? Proportion of men who text frequently while driving is greater than the proportion of women who text while driving. Women who text frequently while driving. Text frequently while driving. Okay. All right. So that's that. Okay, and then the rest is up to you. Take it home. Thank you so much for listening. This has been 8.31, and 8.32 will be posted soon. I'll see you in class today, online via conference. See you soon. Bye-bye.